Okay, so I normally insist in saying that we're not a tech startup, we're a science startup, because we actually started at the science side of things. We had, so to say, nice results in a research project that run in Austria. That's where I come from and where the company is actually located. And we had so nice results with this very peculiar research project that we decided that it would make sense to base a company on that and to use the possibilities and flexibilities of companies to actually develop this further. So the project was called CEPT, which is an acronym for Cortical Engine for Processing Text. And the very initial aim was to find a way to feed text into the HTM, which is the hierarchical temporal memory system that has been developed by Jeff Hawkins and his team in the company Numenta that is working on this. So the HTM is a sort of a neural network without being a neural network. It is actually the model of the neocortex. It tries to model the functional abilities of the neocortex and tries, while doing this, to fully respect the biological background. So as a contrast to the more traditional approach to neural networks, which I think are more, let's say, a mathematical way of looking at things. So the theoretical neuron in a neural network has very little in common with an actual biological neuron. So Jeff's goal was actually to find or to analyze the way how the actual neurons and the actual neocortex work, and to basically distill the functionality out and to capture it in a sort of a machine learning approach in very general terms, to have the processing be similar. So I'm just going to okay. So he tries to actually model the brain, but he does also not model the brain in the sense like you might maybe have heard the Human Brain Project in Europe, and also there are some quite large initiatives here in the US, where you have in majority two approaches. One approach is actually to anatomically analyze how the brain is built. So they have extremely sophisticated ways of following the course of a neuron and the axons and the dendrites with volumetric methods where they actually can figure out where are neurons touching each other and forming synapses. It's really fascinating if you see what they're able to do at this nanoscale level. The point is they will have some work until they have the whole sort of network gathered. And I'm not really sure that by just having the complete plan, you would have actually a better or a finite understanding of what the thing does. So if you would imagine a microprocessor and you would have a complete wiring diagram of all the transistors that you have in it, you would not necessarily know what the microprocessor actually, or how it is actually performing. You will have some ideas on patterns that reoccur in this engine, to actually understand how it works, that teaches you the theory behind the instructions, and then you can simply, by knowing the theory behind it, fully apply it. So the second approach that is used is a more functional approach, is the MRI, where you get certain stimuli to people who are actually measured by their brain activity, and there you can correlate the stimulus with the reaction in the cortex, which is also very sophisticated, very interesting, and very to know. But also, I think really find out the theoretical working of the neocortex still might be complicated by this. So I think all of these approaches are extremely important because they need all of to actually craft a theory that accommodates all this data. But
Jeff obviously has the main focus to work on the theoretical level, try to understand why you find certain structures and how they work together. So to me, it was very convincing because it is a very elegant and at a point simple concept that is behind it, and it allows you basically to take any phenomenon that you have at the level of the cortex, and just by taking the constraints of the theory, analyze it and find some sort of explanation why this happens in that way. So we had this idea that the features that are provided by this kind of networks, by the HTM network, would be very interesting in the context of natural language processing. So features are, for example, the ability to make predictions after having seen a certain number of inputs. The system is able, after training of course, to predict what next input could arrive there. Another feature is the feature of abstraction of data that comes in more or less the same way how you would expect it to happen in language. So there are a lot of similarities. And of course, the reason for that is because language is basically a product of brain activity. So there has to be something in the brain that actually creates a language, and there has to be something that actually understands this language. So if we better understand how the neocortex, and I think that language actually originates from the neocortex, and specifically, if we have an idea how this works, we will definitely have a better idea on how language works per se. So the goal of this project was basically a very technical one, because there was this fundamental problem that you can easily feed numerical data into a neural network. So this is a straightforward approach. But if you have symbolic information, that is not obvious. So if you have a string of text, how would you represent that string in a way that you can actually present it to a network that needs one thing, namely that two things that are similar in reality have to be similar in the representation. If that is not true, the network is not able to learn anything other than maybe some more stochastic information, but it's definitely not able to apply all these advantages and capacities to this kind of data. So in the end, it was about a very fundamental solution that we were looking for, namely the representational problem that we have in natural language processing in general. So until now, and very similar to other sciences, where if you're lacking theory, what you do is you do statistics. You try to collect events, and you try to find patterns and recurrences in these events. And if you do that well enough and long enough, you end up with some data that allows you to basically infer some phenomenon, I would say. And in many cases, this is useful. This is sufficient even for many cases. But if you have a theory, you have one big advantage. You can start to predict. You can say, if that and that and that happens, I know that something else will happen. Or as in neuroscience very often, or also in theoretical physics, as I've learned, you have this even more fascinating prediction where you say, if that and that and that is true, then there must be something like some other part. And then like 5 years later, you have the more experimental scientists actually find this piece, and you know, my theory was not bad. So actually, natural language processing. Wow, okay, yeah. That's another parameter I didn't know. So I lost cost even more time. Well, yeah, so traditionally, natural language processing is mostly done using statistical methods, as we have been doing this for 30, 40 years. These statistical methods are quite sophisticated and in several fields quite good. But something that we discover in many areas is that improvement deltas became smaller and smaller and smaller. So nowadays, if you improve some of the common algorithms by 0.5%, you're already good for a paper. So this is, and we are still kind of quite distant from what you would expect a human-like algorithm to actually perform. Yeah? So all of that was the motivation to go in this direction, to solve this representational problem, to actually feed text into Jeff Hawkins' HDM networks, and to see what happens, basically. So this is a general thing. So everybody's talking about big data. Very few are talking about the fact that a majority, even I would say, of the big data is actually text. And if we don't have an easy way of automated text processing, then we have a lot of in our day-to-day approach. So the concept was to combine our methodology of converting text into something that could be fed into a neural network with the HDM network to achieve something like language intelligence. And here just a couple of aspects where this is important. When you search, you locate documents on the web or locally. If you want to match skills, I don't know if you've ever thought through the problem of having job seekers match job descriptions. What the more commercial applications of this they tend to do is to make classes, to define classes, and they oblige the job seeker to actually say, I'm part of this class, and that class. Of course, this limits both sides. It doesn't perfectly describe the person, and it doesn't perfectly describe the job, but this was necessary in order to make a real matching between the two. Yeah, you can search for products, you can monitor competitors, you can file patents and other business information. You need it for innovation. There's plenty of written information out there that you could use to create something new just by combining existing information. But as there is so much out there, you need a method in improving this and making this more systematic. Then other big problems is the application of work. So I prefer to write the document a second time before I start searching it somewhere on the file server, but it probably takes less time. And then, of course, mining for evidences, security applications, and so on. Current systems have a lot of downsides. Most of the downsides actually come to the, oh, you don't really see the image anyway. Most of the downsides lead to high costs. Yeah, that's whenever something is hard to do and you have to do it or you insist in doing it, you will spend a lot of money afterwards. Very often it's also fragile, so it has to be specialized for a very specific application. It's hard to generalize some functionality, and so on. All things that if your problem that you want to solve is important enough, if your motivation leads to sufficient funding, then you can get quite good results. But to be an average tool like a mobile phone, if a mobile phone would cost the same as a car simply because it's so complicated, probably very few people would actually have one. So the solution, we tried to go really on the very low end of the stack. We started at the bottom, and we tackled this representational problem. So how could we represent text in a way that it would be numeric? And we did this by developing a whole stack of, I would say, traditional NLP processing that allowed us to map a word into a distributed representation. Why this is important is because the HDM theory has one major claim, and that is that every data that comes in or out the neocortex has to have this distributed format. So the name, the actual name, is a sparse distributed representation, which means we are talking about a large many thousand bits large binary number where a fraction of bits are actually set. And the interesting thing is that if you have numbers of this type, they have properties that are not, so to say, common with other mathematical creatures. So one phenomenon, for example, is that each of these bits in this representation has meaning. So a little bit of the semantic of the world or of the universe that we try to represent is tied to every single bit in this representation. If two bits are close to each other, they mean similar things. This leads to the fact that if I drop or I miss a number of bits, the overall meaning of what is represented by this sparse representation will not change much. And these are all, so to say, necessities for the brain processing. I mean, here we have neurons. This is, so to say, very glibbery, unreliable hardware that is trying to do something. So the way how you process this has to be extremely resistant against noise, against any external interaction. No, we actually do not reconstruct the bits. The point is we want to find a representation where we can allow ourselves to say, okay, I do have, I don't know, 200 bits out of 20,000 that contain my information, and I just take 20 of those 200 to actually represent what I'm interested in. And interestingly, if you actually encode the data this way, you still lose nearly none of the information. Very little is lost, much less as you would say you would have a resolution view on the things. So in the same way as it becomes very resistant, you have also this compression factor, because suddenly instead of working with 20,000 bits, which I would need to do in a dense representation, where every bit has to be there, otherwise I misinterpret the whole word, so to say. Here I can subsample and I can end up with, let's say, 20 bits that represent the information that is in reality contained within 20,000 bits. So if we make a graphical representation of these word SDRs, as we call them, so technically we have an engine that allows to feed text in, basically word by word, and each word is converted into this binary creature. And if you sort of plot the image of the set bits, and if you then make some embellishment by making it round instead of squared and so on, you end up with something like that, where every bit basically represents one of the semantic features that describe the word. And what you can see here by these examples, these are actual fingerprints. So the word SDRs, for being easier, we call them semantic fingerprints. So I will keep talking about fingerprints, and I mean the binary representation of words. Here you see, for example, if you compare the word iPhone and the word Apple, that just by looking at it, they look similar. And they look similar because whatever concept is behind Apple and whatever concept is behind iPhone, they have something in common. Same is true, for example, for pop music and Beatles. And even more, words can contain, words can be compared, and you can actually measure the distance between the two representations. You can measure the distance in many different ways. You can take the overlap, which bits are actually shared. You hardly see this here with the little bit more darker bits are actually overlaps of the two representations of cat and dog. And if you compare this to the problem of using the symbolic representation, how could the computer find out that CAT and DOG have something in common? So by looking at the symbols, no way. You need dictionaries, you need thesauruses, and so on. Here in the upper part, you can just by combining them, by comparing them numerically, say that whatever this is, it has something to do with each other. No, we actually do both conversions. Yeah. The only speciality is the only speciality is that when you go the way back, if you have a representation like this and you want to find which word this actually represents, you cannot be sure that this is the exact representation of the word. So theoretically, if there would be one bit different, then it would not. What you do is what is the most similar word. And the most similar word, if let's say it has 98% of the dots in sharing, then it is actually this word that is meant.
It seems like what you would get is a set of possible words.
Exactly. In a decreasing order of how well the matching is. Yeah? And what you will observe, of course, is that the words that you get, they have all something in common. Yeah? So they are contextual words typically. And hopefully, if the demos are up and running again, I will wait on a sign here to show you this. You can actually play around with this. Yeah? So you can bring in patterns, and you can say, show me the most similar to this pattern. Yes?
You mentioned before when you visit, you said before about interpreting the bits, meaning the bits. How do you know what each bit means?
Okay, we can know what they mean, but we don't need to. Because as we are using a distance metric, the specification happens at the level of comparing two things. And that, if you want the definition. We can, of course, there are ways, and we are even trying now to give some graphical tools to investigate this. Basically, every dot that you see corresponds to a context, and the context is a collection of words where the word, where the dot is set, appears frequently in. Yeah? So there is no sharp, definition of a word, but there is, let's say, a cloud of context words in which the word that I'm talking of is usually in the context of. And in fact, that's how we define words ourselves. Yeah? It's always a hard job if someone asks you, tell me what a dog is. Yeah? Then you start off, yeah, it has 4 legs, it has a head. But in reality, if the other person has never seen a dog, it would be a hard guess. Yeah? The only reason why such a concept like dog works is because you have seen a dog, I have seen a dog. Each of us has a, let's say, slightly different perception, but we have both of our maps that we have of this structure have sufficient overlap to agree on it. And this is the convention.
So will there be a dot in there for 4 legs?
No, there won't be a dot for 4 legs, but there will be a dot that, so to say, many, if not all, animals who have 4 legs will have this dot in their context. They will share the context that is specified by this dot will be shared. Does not necessarily need to share it with all mammals. Yeah? If there are animals where people get in doubt, is this a mammal or not? So this one might not have this dot, but in general it will be true. It will be sufficient so that we can talk about mammals.
It sounds almost like a binary Venn diagram where you have different sets of binary overlapping bits.
Yeah, so the point is that although you see that there are things like clusters here, it was also for us in the beginning misleading to think that, then this very cluster here is the dog cluster and that is the cat cluster. That's not really true. What you have, because we have a distributed representation, clusters can be distributed. You can have 3 clusters that are actually characteristic for dogs, and 2 of them might be clusters that are shared with cats, and the 3rd one not. And so it's kind of too complex to actually just apply image analytics, because that was in the first approach. We hoped that now we can image analysis and we can apply this to semantics. That's great. We have enormous amounts of tools right away. But it turned out that although sometimes it was useful, but it was not the principle. So it's not by trying to find shapes that you're actually going to find the one-to-one relationship to meaning. It's distributed. Please.
So
So how do you compare your method with other representations of words by vectors? Normally it's floating point coordinates and not as many coordinates as we do. Below 1,000, hundreds.
How we compare it is yeah. So there are several classes where you can compare. So first of all, what we are using are word vectors. So that's already to be separated from all the document vector-oriented approaches in trying to understand. So these are two families. So we are generically in the word vector family. But most of the word vectors have the problem, how do they create the features? So the typical or more theoretical or academical word vector concepts use, in the worst case, handcrafted features. Yeah, so you have to sit there and say, this word contains that and that and that and that feature, and so on. And if you do that, you can actually do astonishing things with the engine that you create there. But you are far away from working with real data in the real quantity, so to say. So we had really the goal to have something that is unsupervised, where we can throw in, so to say, knowledge data, if you want, text, and where the retina, which is the actual engine that does the mapping, we call that retina, compared to the actual retina that converts images to the brain. So we say our retina converts the words to the brain, and so it had to be unsupervised. This was the main criterion. The other thing is that most of the word vector spaces have no topology, so they don't care where the point is, as long as you know that a specific bit means something. In our brain, a lot of topologies. So nearly all senses, when they actually come into the neocortex, have a structure that has the same topology as the sensory organ in the beginning. So if you look at V1, which is the first level where the visual information appears, this nearly exactly, so to say, reflects the structure of the retina that is projected there. Yeah? So obviously the topology is extremely important, and in our case it is the topology that makes the whole data representation very robust. Because if you imagine you have a cloud of dots down here, for example, if I eliminate one point, this will not change much of the meaning, because there are so many other points that give me a hint to a very similar meaning, that taking away one point doesn't make much. The other thing, and here I come in the next slide, is that it is very hard to do in many of the other approaches, namely to disambiguate information. And as you know, language, the hardest thing of language is that it's extremely ambiguous. It always depends on the context of what the actual meaning of a word is. So if you start with the word apple, for example, it has a okay. Super. You start with the word apple, and the word apple basically has embedded all the meanings that it occurred in our semantic universe. The universe is basically the collection of which we created the original retina of. What you can do is that you take this representation and you say what are the most similar other words that have this structure. And what you will get is the word computer that you have there. And you see that there is really a couple of large patches that actually correlate with Apple. So what I do now is I take this most similar word and I say all the bits that computer has, I eliminate them in my original fingerprint of Apple. And the fingerprint that now remains from Apple, I ask again, what is now the most similar word to Apple? And I find out fruit, because all the computer dots have gone. And I find out fruit has now the most common dots with my word apple. I do the same thing again. I take all the dots from fruit and take them away from apple, and I ask again, and I get rock, because there is the Apple Records Beatles thing, at least in Wikipedia. And like this, actively disambiguate any term, because I could have chosen any other word than apple, and I can computationally disambiguate it without using any thesaurus or any external information. And this is something that I believe is very similar, not to say very typical, on the way how the brain solves this sort of things. Furthermore, as we have binary vectors, we can start to do Boolean operations on them. We can say the dots for Jaguar have a representation. Obviously, Jaguar is again an ambiguous term. I subtract Porsche from it, which to me makes sense, as Jaguar minus Porsche. And what remains, so you can actually, and this is, so to say, a more illustration example, but in principle, what you can do is, in a very naive way, you can compute with the meanings of words. And you can specify, if you want to say a luxury sports limousine, and you want to use that, for example, as a classifier to classify documents, the easiest way of describing this to the system is by saying Jaguar minus title, what remains, corresponds to the pattern of this sports limousine. Next step is that you can create compound fingerprints. You can take a text, and each word in the text gets converted into the fingerprint, and according to the, so to say, capabilities of SDRs, I can aggregate those fingerprints by making a Boolean OR, and I can end up with a fingerprint that contains all the features of my sentence, and this resulting fingerprint exactly like all the other fingerprints. I can disambiguate it, I can compare it with another one, and so on. Everything that we have specified for the worked fingerprints in the first time are true for compound fingerprints or text fingerprints. Now, of course, you have plenty of opportunities. Here you have two sentences: teens like playing good music with their mobile phones. And on the other side, you can also consume chart hits with your notebook. And you see how heavily the overlap is because the two sentences, without sharing a single word, are actually matching semantically. So we can now do things like create search mechanisms. A search mechanism functions by the way that I have a collection of documents. For each document, I create a fingerprint that basically contains the semantic representation of my document. I can, as a query, give an example document, which leads to an example fingerprint. And then by simply calculating the distance between my query fingerprint and all the index documents gives me immediately the closest document to what I was looking for. And this is already much, I would say, more elegant than trying to find strings that match, or to even expand those strings in other strings and so on. This matches the concepts that are compoundly represented by the bits in the representation. And one part that the normal search engines always had a problem with is how do you rank the results. Here we rank the results just by the distance that we find between my query fingerprint and the documents. But I can do it even better. I can tell this semantic search engine, I can give it 5 examples of documents that I'm specifically interested in. And these 5 examples could again be converted into a fingerprint and now are sort of a profile of my interests. And instead of ranking the result set in the distance between query and document, I can now rank it in the distance to my profile fingerprint, which in fact leads to a situation where 2 people with 2 different interests can cast the same query and get 2 different results, as it should be. Yeah, so this is searching. Now, a couple of other practical uses of this is, for example, in social media. Example number 1 is filtering the Twitter fire hose. So imagine this. tweets, and I just want to get those tweets where I have really an interest for. Using keywords is really hard. I mean, if you do the math, you end up that there is really a reason why a keyword-based substream of the Twitter fire hose costs you a couple of $1,000s a month. Yeah? This really needs a lot of computation. What we do is we create a fingerprint of every fingerprint that comes, of every tweet that comes in, and every user who wants to create a substream that is based on the content of the message creates a fingerprint that basically describes the interest by saying words, by giving example documents, or by making expressions like the Jaguar minus Porsche. Print with one message at a time, and suddenly you can serve like 500 users with one server instead of 500 servers for one user, as it was before. Another aspect, LinkedIn, so this is more the profile matching aspect, is you can get from, for example, descriptions that people make about themselves. You create a fingerprint, and from there you could look, for example, for other people who have similar interests, even if they did not actually use exactly the same specification and descriptions that you have used. And yet another one is you can match your interests, your needs that you can describe by documents or purely by typing it in with products, which makes it much easier to create a match. You were first.
It seems like you could take text and apply a simple secret transform.
Absolutely, yeah. If you keep your retina secret, it's pretty hard to find out how it has been encoded. Yeah. Yes.
How much data you need for the to get a meaningful algorithm?
So we wanted to have the general language as a general English language as a starting point, and we used Wikipedia. So in the English Wikipedia you have, and that's how we started, you have something like 4.5 million documents or something like that. But it turned out that if you use too much data and if it's not well enough selected, so to say, I mean, in the English Wikipedia you find as many documents about TV series as you potentially find about remedies or other facts. Yeah? So what we did, we reduced this to more or less 500,000 to 600,000 documents, and that was sufficient to give to result in a retina where you have a hard time finding a word that is not covered and not reasonably represented. I mean, I'm not talking about very special domain-specific terminology, although it's astonishing how far you can go with the Wikipedia. I think, yeah.
So, in the process of generating this fingerprint, how much does the data
mean by the data explode?
If I have to generate a fingerprint data set of 5 million documents, will that translate to 5x?
You mean indexing 5 million documents by creating a fingerprint of that? It takes, I would say, in the order of magnitude the time it takes to make a regular index of it. It rather tends to be faster than slower. A lot of the existing search engine technology and so can be reused. And so we are actually using this. There is a lot of recent research work where people work in the field of binary similarity systems, especially to match images and stuff like that. And they have come up with quite some interesting indexing methods for binary data. But for now, the speed is so far satisfying. We haven't put the effort yet to actually bring this in. But it's good to know that there is some good clues out there to even improve speed.
Did this system support documents that have text and